Hello everyone, my name is Bruno Rodrigues and I will talk about BluePIL, which stands for Bluetooth-based passive localization method. I'm from the Communication Systems Group at the Department of Informatics, IFE, at the University of Zurich. This talk is organized as a motivation, and then I explain the BluePIL approach, show the experiments, and discuss the results and final considerations. The main motivation for this work is to gain knowledge on a specific audience so you can improve the delivery of products and services. The key idea to propose such a work is that if you think in a digital environment, for instance the web, where you can easily track each movement of a user inside a website, track the preferences, which are the most visited pages, and from those pages you can more or less to infer what is the preference of the user, and with those preferences you calculate the key performance indicators, and that will indicate which are, for instance, what is a user looking at, what is users browsing or looking at Google, for instance, and those will give you insights on how you can offer more tailored product or service. This works really well on a digital environment because you can basically track every movement of a user, but the situation is a bit more challenging when we are thinking in the real world, and you have this specific example here of a booth. In the figure you have in a main station, a train station in Zurich, for instance. And the goal here is to understand how your product or service can attract better attention of people passing by, how can you attract more customers, and the challenge is how can you measure such attraction of your product or service in a real world environment. For doing that, we have that we can use mobile devices. We have here, for instance, in Switzerland, that 92% of the population carry a smartphone, and smartphones, they are constantly probing for Wi-Fi networks by sending Wi-Fi probe requests. Based on those Wi-Fi probe requests, we can then infer the number of people passing by each probe request. Can be seen as a device, and one person carries one device. And based on the signal strength of those devices, we can assume whether a device was closer or far away from the booth, for instance, that you are showing during the exhibition. One issue, however, is that many OS manufacturers, operating system manufacturers for mobile systems, Android and Apple, they are aware of such situation, and they implement MAC address randomization. That is, every time you send a probe request, you switch your MAC address in a way that if you send again a new probe request, the device is not recognized. And this creates some issues if you are using such a fingerprinting strategy to infer KPIs to estimate, for instance, how many people are there. And that's an issue with a Wi-Fi based approach. And thinking on that, that comes to the goal of this project, BluePIL, which is to use a very similar strategy, but using Bluetooth signals, packets, in a way that it should work completely passive. That means you should identify and localize individuals without requesting those individuals to be associated with any type of device, which is obviously infeasible if you think in a public environment, for instance, in a public place where people is passing by and want to see whether they are interested or not in your product and service. Important to mention also is that research exists, and there are plenty of work on the device identification and fingerprinting, mostly on wireless. Some of them also based on Bluetooth, but they are mostly active, so you always requesting a device to be associated or be connected inside a local area network, and then you can actively send the packet to the device and measure the response, and based on those signal strengths you can estimate the positioning. But especially for Bluetooth, there is no completely passive approach yet, and that's why that's where the BluePIL fills this gap. It's an approach that works here completely passive way. It has some benefits and also some deficits that we will go after the explanation of the approach itself. Here's the approach, and for that we evolved the architecture or this final design over the time, in which we came up with a distributed and near real-time streaming architecture. And this is important because the collection of the packets, they are sent in different times by each node and sensor, and the streaming architecture make it easier at some point in time to gather together all the collected packets and apply the localization. So it works like this. You have the sensor. In this case we use the Ubertooth sensor. That is a device that will hop between different signals and listen to all Bluetooth connections that are sent by devices passing by. This sensor was connected in this example to a Tinkerboard node that follows the same idea of using a Raspberry Pi. And inside the node, you already implemented two main stages of the device. It is device identification, working on the Bluetooth header and extracting the unique information that allows to identify the device, and then the first stage of the filtering. After you do that, you send the data. All the nodes will send the data to a sink. In this case, we use a laptop. That will do the merging, apply the localization algorithm, and then the filtering. Key with this architecture that is flexible, you can easily add more nodes that would send the collected data to the sink. And it's also cloud friendly, which is something that was required, especially in the context of the project that BluePIL was developed, because this data would be merged with different sources, so you can combine and extract and calculate KPIs to show to show, for instance, whether a person is passing by or a person is interested in how much time it stays close to the exposition. We'll go through each of the steps here. To remind, we have 5. First one is the device identification, then the filtering the signal strength, merging the signal strength in a given time window, estimation the positioning, and applying the filtering. In the first step, we should consider that Bluetooth packet is divided in lowered address part, the upper address part, and the non-significant address part. From those, the LAP is assigned by the manufacturer, and based on this, you can identify who produced the device and what the type of the device. And the upper address part is basically given a unique address that is given to the device, and from those you can uniquely identify the device. From the first, you can identify the manufacturer, and in the lower upper address part and the non-significant address part, you can identify the device. Once the device is identified, it's also important to mention in the non-significant address part, you have a specific frequency in which devices that are passing by, they are checking whether there is another Bluetooth device connected or ready to pair. And based on this frequency that is open, then you can check whether there's a device passing by or not in a passive way. Once they are connected, of course, they will be hopping between different frequencies, and that's why also the sensor need also to hop between those different frequencies. And yeah, you cannot then you could try to either eardrop eavesdrop the connection. In the second part, still done in the device, in the node, is the filtering of the signal that it sends it. It's interesting to observe that we have a lot of noise, typically caused by the multipath fading, if depending on the environment that you are sensing. And the upper part, especially the upper part of the sensed signal, is interesting, and the goal in the second stage was to filter. And for that we used a max-min filter that would allow to retrieve or to filter only the part that is interesting, that will give the data more useful to sense where the device is close or far away. In the third part, the third stage of the system, the first one was related to the device identification. We tried to uniquely identify a device passing by. The second one, we filtered the signal strength, and this is done in different times. And it's also important to note that collecting those different packets might be sparse, because if you are listening to those packets in a passive way, that might not retrieve those packets in a fixed time interval. For instance, if you have in an active approach in which you send a packet and wait for an answer from the device, you can have a measure of signal strength in a given point in time. That brings more challenges to the design of the architecture, because you cannot, for instance, in a given stream, if you do a calculation of a stream in a fixed time interval, which as we do, some of those streams might not have data. And one approach that we came to that is to propose a time window, because the emissions are sparse and also irregular. And as we need to wait for more data to come, we can interpolate the values that arrives afterwards. For instance, after you close a time window, you can interpolate this different data, and then you can merge together in a time window the different RSSI. So this is just a step that we are not filtering. We are just trying to collect together at the sink and to pre-preparation to process, and by process apply the localization algorithm. You should also consider in the interpolation the emission delay, there is a timestamp in which the device is sent, and then you should consider this emission delay to interpolate the different values for the different streams. And each stream here in the figure corresponds to each one of the device. In our example, we used 4 nodes, so 4 sensors connected to the nodes, and all those 4 nodes, they would send the sensed data to a sink that would be placed, for instance, inside a booth. And from this, you could sense and you could extract the localization data that you need. For the localization algorithm, here we rely heavily on the related work. We used a multilateration algorithm that is based on this received signal strength, and then we have the RSSA configured at 1 meter. This is also important one calibration step, and a path loss model considering the distance. And the logic is here that the lowest is the path loss, the higher is the accuracy, because the signal will be usually higher, or that means that the device is typically close to the node or to the sensor. And in the figure that shows how it works, you combine different data from the different sensors, and you do a triangulation, that multilateration of those different signals to estimate whether a device is in a point in time. The solution for that is to come up with a model that you could calibrate at the same time the distance that you consider in the previous equation for every given sensor that we are using. we could calibrate at the same time using the distance and also the log path, the path loss model. An interesting solution for that, also based on related work, was to use the Levenberg-Marquardt equation, because that you can minimize, find a minimal squares for in a given point in time. And this is especially interesting to find a minimal local, because if we are considering that the distance, the far away you are from the sensor, the signal strength will be reduced. You also have the different effects from the multipath fading and the shadowing. And what you need to do is to consider with Levenberg-Marquardt is to minimize those local minimum for the X and Y. This would give you values that are always close in a point in time for X coordinates X, Y, that are closer as possible to the predicted distance loss. And those would eliminate, for instance, values that are caused due to the multipath fading, for instance. And this was particularly interesting to increase the accuracy of the approach. The final step that we also did based on related work was to apply a Kalman filter. And the Kalman filter, once we applied the estimation of positioning on the step 4, we would then look back on history to predict what is the next step, what is the next step that the device would take that would make sense. And the Kalman filter allows you to do that by considering the velocity and the direction of a device, so you can predict what it would be the next location. So the logic is pretty much how it shows in the figure. So you have the ideal path that is done in the figure, that is done in blue, the blue lines, and you have the real measurement points and the prediction of the algorithm of the Kalman filter. And this is particularly interesting because you can smooth, you may not always predict correctly the positioning of the person if the person is doing movements that are completely irregular or have sudden changes of direction. If a person is walking, for instance, in a straight line, and then it suddenly changes when could see something that is interesting or talk to another person, and this, for those cases, the algorithm, the prediction would fail. That closes the 5 different steps that we had in this node sync architecture. And then we did 2 types of tests. One is one indoor environment that we have, important to have many objects inside a room and walls, and these would obviously try to reflect or try to mimic closed environment that you are doing in an exposition, and also an outdoor environment that you have, you could be showing in an exhibition, and would have different effects from the environment. The scenario of testing consisted on those 4 Ubertooth devices connected to the ASUS Tinkerboards, the nodes, that would transmit to a MacBook Pro, serving as a sync via Wi-Fi. To test, we used an Android smartphone that was connected and streaming data to Bluetooth headphones. So just a person that was using a Bluetooth headphone and walking in point that we show in this figure. There's the configuration of the experiments. For the indoor environment, this is the 2.9 meters per 4.2 meters space inside the room, and we had 9 sets of static measurements for 5 minutes. That means that the person walked, stop, and then move it to the next point, and so on. This is inside the indoor environment. In this first experiment, the streaming architecture was not ready yet, so all those steps they were done after the data was collected. in the outdoor environment was already using the streaming architecture. This doesn't change the precision. It would only make it by changing the way you analyze the data. It would only change, for instance, it could scale more the number of nodes in case of need in the outdoor environment. We're using the streaming architecture. In the outdoor environment, we consider this 5 by 5 meters space, and in which you have 5 sets of static phases at 2 points. In dynamic, the static phases are marked with the red X, and the dynamic phases between points the person was walking between a point A or to B for 1 minute. So a slow walk in this sense. And the outdoor environment, as mentioned, has different properties that could affect the accuracy. Concerning the results, we have in overall, we estimated the error, overall mean error in terms of meters, 1 meter for both, which in overall it's a good result. But also we had a few bad ones that can attributed by the multipath fading, and also on the outdoor environment as the conditions of the weather. For instance, direct exposition to the sunlight. It showed in one experiment that makes the signal to vary a lot, and then results are not precise, just not good. Concerning the discussion, we have that the localization method works. This something that was really battle tested in different Wi-Fi and Bluetooth that uses an active approach. So what we changed here is the way you can gather data. And the key point in this project in BluePIL is the streaming architecture that makes it really easy to scale the number of nodes and sensors that you have to sense data. Few negative outliers exist, and those are mostly given to the sparse data that you receive. Sometimes Bluetooth device might not be turned on, in case some people just turn off, and that's something that you cannot avoid. And something that could be improved a lot is that the performance of the sensor, the Bluetooth, is flaky. It's not the best sensor to use. But it's a quite affordable sensor, and something that we saw that some sensors, they might achieve a very high price. The Bluetooth might yield usage of Bluetooth might yield in different results. So we have a limited sensor and external environment effects, as we mentioned. As a summary here, we have that Bluetooth approach, especially that are based at Bluetooth tracking approach, especially passive ones, is something that was not existing before, and BluePIL fills this gap with a distributed node sync approach that is scalable, works in a fully passive approach, and identify and localize individuals. As a next step, I would like to summarize here to point out that we could use different sensors. In this case, the LCs here, for instance, could come up with 20,000 Swiss francs. That would be roughly similar to 20 at price of today, around the same thing in US dollars. And that could yield more performance in the tracking. But on the other side, if you rely on a fully passive approach, also relies on how much data you receive. So there is this trade-off. But in ideal, the approach is ideal to combine with different wireless sources approach, and that would help to increase precision of tracking. With that, I would like to conclude. Thank you very much.